So far, we've represented functions two ways, using rules and using tables. Now, those are really useful in different situations, but what they're not very good at doing is allowing us to actually see the way a function behaves. For that, we've got our next representation, the graph. So, to connect the idea of functions and graphs, we're first going to talk about ordered pairs. An ordered pair, which we write as two numbers in parentheses like this, though I'm using variables right now, and you'll see why in a moment, those variables are x and y. That can represent the value of two variables, which are typically x and y in that order. Or they can also represent the coordinates of a point on the coordinate plane. Now, a function, as we've already established, represents a particular type of relationship between values of x and y. Remember, x is our input and y is the output. Well, if we take those pairs of inputs and outputs and plot them as coordinates, we can represent our function by plotting a graph on the coordinate plane. And the best way of seeing how this works is actually to just go ahead and make a graph. So in our first example, we have the function with the rule y equals 2x plus 4. So we can go through and fill out this table. We've done this before, but remember, x is our input. So we take our input, -3, multiply it by 2 would be -6, plus 4 is -2. And then we can go through and fill out the rest of the table. Now, each entry in our table where we have an input and an output can be written as an ordered pair. So, where we have input x equals -3 and output y equals -2, that's the ordered pair, -3, -2. And that can be plotted as using those as coordinates. So remember, the first coordinate is the x coordinate. Now, positive for our horizontal coordinate, x, is to the right, but we have -3, so we're going to go to -3. Then our y coordinate is -2, so we're going to go down 2 units. Next, we have -2, 0. So that lands here on our coordinate plane. Then we have -1, 2. That lands here on our coordinate plane. Then we have 0, 4. That lands here. Then we have 1, 6. So 1 to the right, 6 units up, which is there. Next is 2, 8. So 2 across to the right and 8 up. And finally, we have 3, 10. So that would be 3, 10. Now, you may notice something here. All of our points are lying in a straight line. Well, one key thing to remember here is our table doesn't actually show every value of the function. There's some limitations here. We could still evaluate this function at x equals 0.5, for instance, but I don't have a 0.5 entry in the table. But that's okay. We can actually represent all those values in between our points using the graph if we connect them all up. And because this is a straight line, I'm going to use a ruler. And then the other thing I'm going to do is draw an arrow on either end of my line, which is to show that this line, if we had more table and more graph, this line would continue in either direction. And there we have it. We have our function represented using a graph. So every time we have an input, let's say our input is 1 here, then we can go up to the graph and find the value of the output, which is 6. Notice that matches what we have in our table, 1, 6. Okay, let's do another example. So our function is y equals x divided by 4 plus 1. So negative 4 divided by 4 is negative 1 plus 1 is 0. Negative 2 divided by 4 is a negative half plus 1 would be 1/2. I'm going to write them as decimals here for convenience. And we can go through, assuming we remember how to do this from our last couple of lessons, we can fill out the rest of the table. So we can plot these as coordinates. Now, unlike before, we're not going to take the time to write these out as ordered pairs because we can just read them straight from the table. So firstly, we have negative 4, 0. So that's the coordinate, negative 4, 0. Then we have negative 2, 0.5. Now, I don't have a grid line through 0.5, but we can be reasonably accurate and put where we think halfway up the grid is. Then we have 0, 1. Then we have 2, 1.5. Maybe we should be a little lower than that. Then we have 4, 2. And then lastly, we have 6, 2.5. So that is there. Like before, our points form a straight line. So, because we want to represent all the values that we didn't include in our table, we can connect them using a ruler. Straight through like that. That went a little further than I intended, but that's okay. Let's draw an arrow to show that that line keeps going on either end. And there we have it. We have our graph. Notice there's some similarities to these two graphs. They're both straight lines. But there are some other characteristics about them that we can understand. And we're going to go into a lot more detail of understanding the graphs of linear functions in the future. But let's focus on one particular characteristic right now. And you've probably figured this out already, but we call these functions linear functions. So this is a linear function. And by graphing them, you've probably figured out why. It's because the graph is a straight line. Okay, so anytime we have a graph that forms a straight line, it's going to be a linear function. That is another defining feature of what makes it a linear function. And so why we've been calling them linear functions all along is because of this behavior of the graph. Let's have a look at what we might do to go the other way. If we had a graph, how might we figure out what the function is? Well, we know that this represents a set of ordered pairs. In fact, let's mark some of the coordinates we have here. So there's one point that lays on the line. I'm choosing this one because that's where a couple of grid lines meet. So that's easy to tell what the coordinates of that point are. Here's another one there. And there's another point there. and there, and there. Now remember, every point along this line is an ordered pair which represents an input and output of the function. But I'm choosing the ones that are on the grid lines because they're the ones that are easiest to tell what their values are. So this point here has coordinates -4, 5. So those are our input and output. This point has the coordinates -2, 4. Again, those are our input and output. Then we have 0, 3, 2, 2, and 4, 1. So we've taken our graph, and just by looking at the coordinates, we've made a table. Now we already know how to turn a table into a rule. So let's go ahead and do that. Let's see how x is changing. So from -4 to -2, we're adding 2. Then we're adding 2, adding 2, adding 2. This was somewhat convenient because we always picked our points going up 2 at a time. If we look at what y is doing, we are subtracting 1 each time. So from 5 to 4 to 3 to 2 to 1. So our rate of change, which is m, is change in y over change in x, which is -1 over 2, or -1/2. So that means our rule looks something like y equals -1/2 of x plus b. Now, we need to pick a entry in our table to help us figure out what b is. And I'm probably guessed from last lesson what entry I'm going to pick. We have one where x equals 0, so that's the one we're going to use. So, substituting in these values into our rule, we have y equals 3, x equals 0, so that's -1/2 times 0 plus b. So this is really 3 equals 0 plus b, which only works if b is 3. So our rule, y equals -1/2 of x plus 3. Now we should check that this works and it really does match the graph that we started with. So let's pick an input. Let's say 4. So for the input of 4, we have -1/2 times 4. Half of 4 is 2, so that's -2. So -2 plus 3 is equal to 1. If we check our table for the input 4, we really do have the output 1. And we should be able to go through and pick any point along this line, and it will match this rule. Let's do this again for a second example. So again, to make things easier, we're going to pick the coordinates of points that fall on our grid lines, because those are the points that are the easiest. I mean, they're whole numbers, that's why. If our line is laying on grid lines, then their coordinates are going to be whole numbers. So this one here has the coordinates -3 and then -6. So that's our first entry. -3, -6. The next one, our coordinates are 0, -4. Then this point has 3, -2. And then our last one has 6, 0. Okay. Let's look at our changes, because that's what we need to do first to find our rate of change. So from -3 to 0, we're adding 3. And somewhat predictably, because our points are evenly spaced along the line, our changes are just going to be the same, +3. for y to go from -6 to -4, we're adding 2. And then we're adding 2. Then we're adding 2. So the rate of change, m, is equal to delta y divided by delta x, which in this case is 2 divided by 3, or 2/3, because this isn't going to simplify. So y is 2/3 of x plus some number that we don't know yet. Now, let's pick an entry in the table, and, well, you can probably guess what my preference is. I'm going to use x equals 0. And I really do hope you figured out why I like using x equals 0 by this point. But x equals 0 corresponds to y equals -4. We can also find this on the graph. When x equals 0, we go down to -4. So that means substituting into the rule, y is -4. We've got 2/3 of x, which is 0. And then we have b. -4 doesn't need evaluating, but 2/3 of 0 can be evaluated to 0. This is 0 plus b, which only makes sense if b is equal to -4. So our rule is y equals 2/3 of x. Now we could write plus -4, but it's more concise to write take 4. Like before, let's check that this does actually make sense. So we'll pick an input, let's say 3. 2/3 of 3 is 2. So then we have 2 take 4, which would be -2. And if we look on our graph for the input of 3, now the output is indeed -2. So at least for that point, this rule does seem to be correct. And if we were to check everywhere else along the line, this should really be the correct answer.